We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
Spacecraft now to full internal cooling. The cooling load has been shared with the ground cooling. T-minus 90 seconds and counting. T-minus 90 seconds and counting. At T-minus 1 minute 15 seconds, the spacecraft, as we move down through the count at the T-minus 17-second mark.
Welcome. You are about to embark on a voyage to the Earth's moon. Only a few astronauts have ever actually taken this trip, and it usually lasts 3 days. But through state-of-the-art visualization technology, we will complete our journey in just a matter of minutes. As we arrive at Kennedy Space Center's Vehicle Assembly Building, let's take a look at one of the 2 Ares rockets NASA plans to use in their upcoming mission to return to the moon. The 2 rockets, called Ares 1 and Ares 5, will carry everything we need for our mission. Us, our spacecraft, our life support supplies, and our lunar lander.
The cooling load has been shared with the ground cooling. T-minus 90 seconds and counting. T-minus 90 seconds and counting. At T-minus 1 minute 15 seconds, the spacecraft batteries will be turned on for launch.
This is the Ares 5 rocket. It can carry nearly 100,000 pounds to the moon. That's as heavy as 4 school buses. The entire assembly stands more than 360 feet tall. The long tubes you see on either side of Ares 5 are reusable solid rocket boosters, the same boosters that are used on the space shuttle. But the Ares 5 central core more closely resembles the Saturn V rockets that carried the Apollo astronauts to the moon in the 1960s and 70s. We need a rocket large and powerful enough to escape Earth's gravity and to navigate our way to the moon, nearly 250,000 miles away from Earth. With a rocket like this, we are ready for our trip to the moon.
17, guidance release. 15, 14, 13, 12, 11, 10, 9. We have ignition sequence start. The engine's now building up to 7.7 million pounds of thrust. We have launched and we have a liftoff. Turn on, moving back.
As we leave Earth, we can clearly see the bright haze from the atmosphere, the protective layer of air that surrounds our planet. This amazingly thin layer contains the oxygen and nitrogen that we breathe, plus the carbon dioxide that fuels the plants. The atmosphere also contains clouds, storms, rain, snow, and just about any kind of weather that you can think of. Our flight path will take us one full orbit around Earth before we are able to change our trajectory for the moon. We're heading east, and below is the Atlantic Ocean, which contains the Earth's most precious resource, water. Nearly 3/4 of the Earth's surface is covered with water. Even though the Earth is covered with water, only 1% of it is fresh water that we can drink. And since we know that all living things need water to survive, well, that makes water one very important resource on our planet. We're approaching the western coast of Africa and the vast expanse of the Sahara Desert. The Sahara is as large as the United States. Not much water here, but watch as the dry Sahara gives way to the rich green jungle of the Congo. And as we pass the western border of Tanzania, if you look south, you can get a glimpse of some of that rare fresh water in the giant lakes that outline its border. We are flying over Madagascar now and approaching the day-night boundary. What is the day-night boundary? Well, it takes the Earth exactly 1 day or 24 hours to rotate on its axis. This rotation carries the planet from daylight into darkness and back again. And we can see this day-night boundary line from space. Underneath us is the immense darkness of the Indian Ocean, virtually uninterrupted by islands or civilization. But as we approach Australia, you can see its western coastline dotted with lights. And where are these lights coming from? Cities. And where there are cities, there are people, lots of people. Even from space, the signs of life on Earth are visible. We are now traveling over Earth's largest ocean, the Pacific. You may notice the clouds below appear to be illuminated. And what's lighting up the clouds? The sun, of course. Light from the sun gets reflected off the moon, which in turn illuminates the clouds. We can also see our own Milky Way galaxy arcing through the nighttime sky. Though it looks like a band of white light, this Milky Way galaxy contains billions of stars, many like our sun. A gorgeous sunrise greets us as we move from darkness into light. A sunrise from orbit, the kind of sunrise most people will never see. We're now crossing the Gulf of Mexico, on our way to the place where we started our journey, Cape Kennedy. There's Florida's panhandle in front of us, and it's time to leave Earth orbit and follow our trajectory toward the moon. A trajectory is a path or a course created to get from one place to another. Plotting that course through space is a bit tricky since everything in space is moving. Not only do we have to figure out how to get to the moon, but we have to determine where the moon will be when we arrive, not only in its orbit, but also in its rotation. We will need to fire our engines again, just as we did taking off from Earth. The amount of energy we need to push us out of low Earth orbit onto our path to the moon is small compared to the energy that it took to get us into orbit. We can see the moon rising ahead of us now, and it's time to fire our engines. We are now on our way to the moon. Let's use our spacecraft's technology to take a look at a few things that we wouldn't normally see out the window of an actual ship on its way to the moon. For example, notice the positions of human-made satellites around Earth. Those in high orbits are often used for communication. Anyone ever heard of GPS? Well, these are the satellites that enable us to locate and communicate with people all over the world. The satellites in lower orbits, closer to Earth, are often used for things like monitoring the weather. In the last 50 years, we've put a lot of stuff into orbit around the Earth, and these devices have become an important part of our daily lives. Let's step outside and take a look at our own spacecraft. Here is our craft. While it continues its journey to the moon, we can take some time to explore the environment in space around Earth. Most people think of space as being totally empty, but the space between the sun and the planets, even between the Earth and the moon, actually contains many tiny particles that we can't see. Most of these particles come from the sun. They fly through space so quickly that if a burst of them were to hit a satellite, a spacecraft, or especially an astronaut, they could cause a lot of damage. These particles make up what we call the solar wind. Fortunately, on Earth, we are protected by our magnetic field and atmosphere, which work together to deflect and absorb this barrage of particles. We can't actually see the magnetic field with our naked eye, but we can detect it with our instruments. When we do, we find that it's shaped like this, rounded on one side with long, drawn-out lines on the other. This is called the magnetosphere, but it isn't really a sphere like a beach ball, because the solar wind pushes on the side closest to the sun. On the side away from the sun, the Earth's magnetic field stretches out, sort of like a tail. Almost all our satellites remain inside the Earth's protective magnetic field. Any satellites that orbit more than about 43,000 miles away from Earth are outside the protective influence of the magnetosphere and could suffer damage from the solar wind. You'll notice that the Moon's orbit is mostly outside the Earth's magnetic field, as represented by the line you can see here. So on the Moon, astronauts could be exposed to potentially dangerous radiation from the sun's solar wind. Here comes our spacecraft. That's the Earth in the distance. Closest to us is our lunar lander, the craft that will actually land on the Moon. Those things sticking out of it are the footpads, which will actually touch the lunar surface. We can also see the lander's thrusters, the rockets that will help slow the craft's descent by pushing against the Moon's gravity. This will ensure a gentle landing. Thrusters will also lift us off the Moon when our mission on the lunar surface has ended. As the spacecraft passes in front of us, we can see a blue cylinder with a cone-shaped unit below. This houses the crew module. The large thruster and engine on the crew module will be used to rocket back home, and the cone-shaped part of the spacecraft will complete the final phase of the return trip, parachuting through the Earth's atmosphere at the end of the mission to land in the desert in the western U.S. We're getting close to our destination now, So let's rejoin our spacecraft to experience the rest of the trip like astronauts. As we approach the moon, we begin to see details that were only faintly visible back on Earth. The moon's surface is almost uniformly gray. It has no oceans, in fact, no water at all, no green plant life, and certainly no city lights. The darker, flatter areas you see on the moon's surface are called maria. When astronomers first looked at the moon and saw these large dark patches, they thought they were created by water. They called them maria, from the Latin word for ocean. But when astronauts actually visited the moon and brought back samples of this terrain, we learned that the maria were created by volcanic rock that oozed out of the moon's surface billions of years ago. If you look to the horizon, you'll notice that this line looks much sharper than it did on Earth. This is because the moon has no atmosphere, and because of that, conditions on the moon can be quite severe. On the sunlit side, temperatures can reach 250 degrees Fahrenheit, and the nighttime side can plummet to minus 250 degrees Fahrenheit. Without the proper protection, none of us could survive those boiling hot days and freezing cold nights. We are now in orbit on the far side of the moon, the side that never faces the Earth. Because the moon rotates at the same rate as it orbits the Earth, we always have the same side of the moon facing us. The side that faces away we call the far side. On the far side of the moon, we can see a lot more craters. Craters are formed by asteroids and comets hitting the lunar surface. Most of the craters were made a long time ago, but some are more recent. How can we tell? Look for craters inside of other craters. We are approaching the edge of the largest crater found in the solar system, and it's right here on our moon. Known as the Aitken Basin, this supercrater is nearly 7 miles deep and over 1,500 miles wide. That's about half the width of the entire continental U.S. As we pass over the South Pole, we can take a look at the day-night boundary on the moon. The moon has a day and night cycle just like Earth, but the moon's day and night cycle lasts almost 30 days. That's a long time compared to the 24 hours in Earth's day and night cycle. Let's begin our preparation for landing. Today, we're headed for the Apollo 17 landing site. This is where humans last walked on the moon, December 11th, 1972. On our final approach, we pass over the mare known as the Sea of Tranquility. This mare was made famous by the crew of Apollo 11, the first people to walk on the moon back in 1969. We are headed to the far side of the mare. As we approach, you'll notice that this part of the moon looks very detailed compared to the surrounding area. This is because astronauts have brought back detailed data that tells us exactly what this region looks like. The ridge of mountains ahead of us includes peaks that would dwarf most mountains on Earth. This is because the moon's lower gravity allows for much steeper and taller peaks than we have back home. The South Massif looms ahead of us, and the North Massif beyond. We will be heading to the valley in between them at the Taurus Littrow landing site. Imagine what the Apollo 17 astronauts must have felt seeing this place for the first time.
Over. Oh, are we coming in? Both babies. Stage through 9,000. Stand by for pitch over, Jack. 8,000. I'll need the probe. I'll give it to you. There it is. Proceeded. And there it is, Houston. There's Camelot. Wide on target. I see it. We got them all. 42 degrees, 37 degrees, to 5,500. 38 degrees.
Dellinger, you'll go for landing.
42
Welcome to the moon. We can now see what our lunar lander looks like resting on the moon. As you descend this ladder to explore the lunar surface, look around. No people, no water, no life anywhere. Just you and your spacecraft. This terrain dates back to the early history of the solar system. Nearly 4 billion years ago, a giant asteroid or comet struck the moon. The impact formed the two ranges of these enormous mountains called the North and South Massifs. The valley we're in collapsed soon after, and then lava flows from ancient volcanoes seeped into this valley. We have simulated a trip to the moon, but perhaps someday you'll have a chance to experience the real thing. NASA is currently making plans for a return trip to the moon to further explore its geology and identify resources to support future space exploration. This program will give astronauts the chance to learn how to live in space while still relatively close to home, preparing us for future destinations such as Mars. Maybe one of you could be part of that journey.